Okay guys, in this video lesson we're going to introduce solution chemistry to you guys and get it rolling on our next unit. Alright, so here we go. First thing, if we're going to do solutions, we need to get some terminology down. Now, there will be lots of different terms in this unit that we use, but two of the key ones that we're going to use a lot is the word solvent and solute. Okay, so they get changed around a little bit, but ultimately the solvent is the thing that creates the dissolving. Okay, so almost always waters are solvent. Okay, not always, but almost always water is going to be our solvent when we talk about things in this unit. Okay, so we say that the water does the dissolving. We also give water the term universal solvent because it is used pretty universally through industry and science, that kind of stuff. We use it for a lot of things in terms of dissolving things. Okay, now technically speaking, if you're looking at a solution and which one is the solvent versus the solute, now the solute we say gets dissolved. Okay, so it's the particle that gets put in and gets dissolved away. So in your typical example, you know, water's your solvent and like salt you put into it is your solute. Okay, that kind of stuff. Now, if you look at it in terms of official definitions, however, the solvent is whatever you have more of, whatever you have less of is your solute. Because there can be a scenario where maybe we put 60% of something in with only 40% water. In that case, if water is only 40%, it's the solute, it's not the solvent. Okay, so if we go over to this picture and we take a look, all the little blue marbles inside of here would be the solvents. All the little orange ones would be the solutes. Okay, does it make a difference of what their polarity is, that kind of stuff? Yeah, sure. But at the end of the day, we have less orange, we have more blue. So orange is a solute, blue is a solvent here. Okay. So those are our first two terms. Make sure you kind of keep them separate, because if I talk about what happens to the solute versus the solvent, you got to make sure you know which one I'm talking about in our scenarios that we're going to develop throughout this unit. Now, one other thing we need to talk about in terms of solutions is what types we have of these different types of solutions. Okay, most people, if I say what's a solution, students would tell me, oh, it's like sugar water or Kool-Aid or pop or milk or, you know, whatever they think of coffee that has, you know, a liquid and some sort of solid has been dissolved in it. Okay, and that's a very typical, very common, very normal type of solution. However, I want you to expand your definition of solution. So when we look at solutions, actually a solution is any time you are physically mixing two or more substances together that stay in that mixture and create a single layer or a single phase. Okay, so if we mix multiple things together and they don't settle out, they don't create a suspension, they don't create layers after you leave them sit, that's a solution. So actually you can have a gas with another gas be your solution. You can have a liquid that dissolves in a gas is your solution. Okay, so air is a great example of a gaseous solution. Humidity in air is a great example of a liquid dissolved into a gas because water vapor is dissolved into our air. Okay. You can also have liquid solutions, and these are you're probably more comfortable with because your solvent here is a liquid. And you get all three states here. We have gas, liquid, and solid. Now you'll notice for gaseous solutions we couldn't have a solid solute. That's because solids would always eventually phase out or fall out of solution. So think of like dust particles in the air. Eventually they're going to settle out and land on things, and then you get to dust your house. Okay, so they don't really create solutions with a gas solvent. However, you can get solids to suspend into liquids. Some examples here with the gas and liquid, all our carbonated drinks. Okay, oxygen that you bubble into your fish tanks, just normal oxygen in the oceans and the waters. It's all gas to liquid. Liquid to liquid, vinegar. Vinegar is actually acetic acid dissolved in water, ethanol dissolved in water. And then solid to liquid, this is one that probably is the most common, you know, we take like salt water and those kind of things. Now, the last one is the one that is probably the most, you know, interesting to think about, that you can have solid solutions. Now, I'm not saying you can take two solid things and grind them together and make a solution, okay? The way you make solid solutions is you create them in the liquid phase and then you let them solidify, okay? So you can have a liquid to solid, and this one's kind of interesting, dental amalgam. And what that is basically stuff they make for like dental fillings, the metallic dental fillings, the ones that have like kind of a silver look to them. What they do there is they actually dissolve mercury into silver. And once you do that, the mercury is now bound to the silver and it's safe anymore. So it's not like you're going to get mercury poisoning or anything. And that's your silver filling, is you doing that. Now they do this in a liquid phase, and then they actually let it cool down, and then that's when it cools down is what it actually gets into your teeth and hardens that way. Okay, and then solid to solid. Okay, something like sterling silver would be an example of that, where you create this. Now, the solid-to-solid solution, another word for that is an alloy. Okay, so if you want to, write the word alloy right down here, because anytime that we're doing these, we're actually creating alloys. Okay. Now, last but not least, when we use the word solution, okay, we know that means we're mixing things together to get a single phase. That should bring you back to another term we used earlier in the year. Okay. So if you have things mixed together and they create one phase or one looking substance to that, we have a homogeneous mixture. Okay, so we want to make sure we link that term back to us again, because it might be one that you haven't thought about for a while. Okay, if you remember, we actually said the word solution and the word homogeneous mixtures are interchangeable. So anytime we're talking about solutions, we can say the word homogeneous mixture. Anytime we say homogeneous mixture, we could actually say the word solution instead. Because if you look, we can get any type of homogeneous mixture between lots of ways to create solutions also. Okay. Now, the next part of this is how do solutions, or how do solutes dissolve to make a solution? Because we need to have a dissolving process, all right? And there's two steps to the dissolving process. So when you dissolve something into, let's say, water or a solution of some sort, you always undergo two different phases of the process, okay? So step one is solvation, okay? Another word for that is disassociation. Now, if you disassociate yourself from somebody, that means you separate yourself from somebody. So maybe, you know, you have a girlfriend or a boyfriend or a significant other, and you no longer want to be with them. So you're going to disassociate yourself with them, or you're going to separate yourself from them, okay? Solvation is just a more fancy word for that. Now, what happens is, in this case, the first step is you break apart. And then once you break apart, then you go down to step number two, which is called hydration. Okay, and any good breakup, okay, once you've disassociated yourself from your ex-partner, and now you're going to go on, and to do that, you need to have support, right? You need to have support from your friends, the people around you. They need to surround you and give you support as you're going through these tough breakups. And that's the hydration step of this process, right? So once you've broke apart, then water molecules surround that thing that's been broken off, and they stabilize it, okay? That stabilization piece is very important, because if water can't surround it and stabilize it, it will just rejoin up again, okay? And we've all seen that happen, right? If you break up with somebody and then they get back together, and they break up, they get back together, it's a really, really ugly cycle. So two steps to dissolving is very much like a breakup. You know, first you break apart, solvation, and then you undergo hydration, where water surrounds you, or you get the support from your friends to maintain that breakup, okay? Now, the big piece of this, the other side of this, is how things dissolve. And we want to make sure that we make a distinction between ionic compounds and covalently bonded molecules, between those two different ways that they do that. So over here, it's not listed here, but we should write down the word covalent molecule here, because this is talking about covalent molecules and how they dissolve. When you dissolve a covalent molecule, and these are examples of sugar molecules, actually, if you take a look at them. So here's a sugar molecule, here's a sugar molecule. I circled this one in green, here's a sugar molecule. Here's another sugar molecule, here's another sugar molecule. You'll notice that over here, we kind of show them in their solid side, and they're being dissolved by water. Once they are solvated or disassociated here, they do get surrounded by the water here and hydrated. But for covalent molecules, and here's the key, they stay together. Okay, notice how the entire molecule is still one packet or one pack. Okay, so the molecules do not separate apart into ions or different pieces. They maintain their original molecule. All that gets broken are intermolecular forces. Okay, again, when you're dealing with solutes of molecules, all you break is those intermolecular forces between there. So those dipole-dipole forces get broken here. Okay. However, for ionic compounds, the dissolving is a little bit different, because for ionic compounds, we actually get separation between ions. And we have a little video just for you guys to see that part.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
So what we see here is we have our positive side of the water molecule surrounding that. and then we have a negative side of the water molecule surrounding this one, okay? So the key difference between molecules and how they dissolve is they stay together, where in ionic compounds, we actually split into individual ions, okay? That becomes very important in this unit, okay? This concept of molecules staying together, ionic compounds splitting. Because when these split, now we have mobile or movable electrons, and we have mobile and movable charge. So there's going to be a very big difference between how these things are going to interact with electrical conduction and temperatures and all kinds of stuff, because they are not charged. Here we have charged particles in solution. Okay, so take home, molecules stay together. Ionic compounds, they split apart into their individual ions, creating mobile charged particles in solution. Okay, guys? All right, so that brings up our very last topic for this video, which is like dissolves like. We know that in our solutions that polar things dissolve with polar and nonpolar with nonpolar. That's from our last unit. Okay. What we want to talk about is what happens when you may not get dissolving to actually occur. So in some ionic compounds, okay, the crystal lattice that holds them together, that interlocking mechanism of the crystal lattice, is actually stronger than the attractive forces that water has to pull them apart through the ion-dipole interaction. So if you have a crystal lattice that actually is too strong, water can't break it apart. If it can't break it apart, it will not dissolve. Okay, so it's a pretty simple concept that basically one is stronger than the other. So if someone ever says, well, why does this ionic compound dissolve and why that one doesn't? Well, the one that doesn't dissolve has a stronger interlocking mechanism, or it has a stronger crystal lattice. It just takes too much energy for it to happen. Okay, the only way that we can determine that is to go back to our solubility rules. Okay, so those are on the back of our periodic table, so make sure you go back and check those. So when we're talking about dissolving ionic compounds, we want to reference those. Will this dissolve or not, based off of those rules. Okay, and then can we get things that aren't supposed to dissolve together? So for example, can I get oils and fats to dissolve into water? Okay, now the answer to that is absolutely yes, because if that wasn't the case, half the food products that we have and we eat wouldn't exist or wouldn't work. You'd always have layers and that kind of stuff, and it would look ugly and you'd think it's gross and those kind of things. So if you want to create or force a non-polar thing to dissolve into a polar substance, to make that happen, we have to find another molecule. We need a third party. We need a mediator to bring the two parties together to get them to actually, so they'll link up and they'll actually interact with each other. To make that happen, we use things called surfactants and emulsifiers. Okay, so really, emulsifiers and surfactants, they're the exact same thing. They're the exact same mechanism, the exact same process. But emulsifiers are a term that we use in the food industry in terms of a food type product, and surfactant is things that we use that's not part of the food industry. Okay, in terms of those two different terms. So both of them link the two together. Now, the way it works is you have this molecule that's really long. So you see down here in this image, we have this really long carbon chain. This entire carbon chain is nonpolar. But on the very end, way down here, we get this really strong polar end, almost to an ionic state. Okay? So because this is so long, we actually generate a two-sided molecule, where one side can act like nonpolar and the other side can act polar. As a result, this nonpolar end can attach to and it can work with all the nonpolar things. This side can attach to and work with water. So it creates a link, or kind of like a coupler in the chain between nonpolar things and polar things. Here's a quick video on it, and then we'll wrap up.
Surfactant molecules exist in aqueous solution as micelles, clusters of surfactant molecules. The long nonpolar chains of the surfactant molecules are pointed inward, and the polar charged end groups point outward into the water. In solution, water molecules interact with the polar negatively charged ends of the surfactant molecules and with the sodium cations that provide charge balance. When a microscopic oil particle on an item of clothing is exposed to this solution and there is agitation, the surfactant molecules become embedded in the oil droplet through the hydrophobic, oil-loving hydrocarbon chain part of the molecules. As more and more surfactant molecules become embedded in the oil droplet, it is lifted from the surface of the clothing. This process occurs because the polar, charged ends of the surfactant molecules interact strongly with the surrounding water.
Okay, so what we see there then is the idea of the hydrophobic end sticking out, the hydrophilic end sticks in. Okay, now those are some big terms that we really won't use in our unit, but they kind of make it sound real fancy with those kind of things. But ultimately what happens is the nonpolar end grabs the oil, the polar end hangs out in the water, and then you wash it away. Okay, and surfactants, guess what? They're soap. Okay, so that's when you were a little kid and mom said go wash your hands, and then you ran in there, splashed some water on it, came running back out. She turns you around and said no, go use soap. This is why she wanted you to use soap, because the soap is what actually grabs the oils and greases and the dirts and actually pulls it off your hands. Otherwise it just stays there and you just rinse water over top of it. Okay, the soap also acts to kill viruses and bacteria and that kind of stuff, which is cool. But this is the process behind it, is that you need the mechanism or the link between the water and the dirt, the grime, the grease. Okay, it's also why we use laundry detergent, because it pulls the stuff out of our clothes when they get dirty. Okay. All right, guys, we're going to end the video here. In our next segment, we will talk about electrical conduction. Thank you.